Welcome to the Seaward Pat Refresher webinar series. This is session number 6, Advanced Pat Tests. My name is Kevin Smith, I'm Category Manager here at Seaward, and I'm going to be taking you through this Pat webinar series. If you want to connect with me in relation to the content of the webinar, or anything Seaward related, I'm active on Facebook, in the Pat Testing forums, and you can also connect with me via LinkedIn. So today, the agenda for the webinar, obviously the Pat Refresher series of webinars, we're now through onto session 6. So this is the 6th week in a row we've been doing this. And the Pat Refresher series has been really well received by everybody. And we've been really pleased with the number of people that we've had turn out for these sessions. So session number 6, we're going to look at advanced pat tests. Last time in session number 5, we looked at the basic pat tests, the core pat tests. Now we're going to look at the advanced tests that we can actually add to test a wider range of equipment. So we're going to review again the essential tests, the list of tests that we carry out, so we can see how the basic tests and the advanced tests fit together. We're going to have a look at the options for testing insulation. We're going to have a look at more detail in what's known as the leakage tests, the protective conductor and touch current tests, and we're also going to have a look in detail at RCD testing. And then to finish up at that point, we'll answer your questions in the Q&A. So the way the Q&A works is using the chat box in GoToWebinar, you can type in your questions as we go through the webinar, and I'll either answer those by typing as we go through, or if it's something that's asked by quite a few people or it's quite a detailed topic, I'll save it to the end and we'll cover it in the live Q&A. So while you're going through, get your questions into the chat box. It's always great to see everybody's questions and interact with people during the webinar. So with that said, let's get started. In the last session, we looked at the basic tests that are applicable to all equipment. In this session, we will look at the additional tests that can be used to fully test a wider range of equipment types. As a competent person, you must understand the range of tests available to you and which tests to apply to verify the safety status of equipment under test. So here we go, we've got the table that we looked at last time, and obviously last time we looked at the basic tests. So every item of equipment you'll see off here gets a visual inspection to start with, so we can take that as read that all items we test would have to have passed a full formal visual inspection before we carry on to doing the testing. Then we've got the basic tests like earth continuity for class 1, insulation resistance, and polarity tests for leads. And then we've got some optional tests in here. So we've got things like the substitute or alternative leakage test, protective conductor current, touch current tests, load tests, RCD testing, and the functional checks. So all of these are the options that we've got in there, and as you'll see, there's a lot of things that are ticked in there as optional. So what we're going to do now is we're going to have a bit more of a look into the leakage testing and the RCD testing to give you an idea of what they are, how they fit together, and how they fit together with, for example, the insulation resistance tests to be able to fully test more complicated equipment and really get into the detail of pat testing, shall we say, from that side of things. So always be aware, although we're talking about the advanced testing here, this table really gives you the overall picture. And as I've said in the previous slide, it is down to the competent person to understand what test they've got available, either in their pat tester or what they can actually apply, and then to interpret what are the appropriate tests to carry out on each piece of equipment to determine the safety condition of that equipment. And we can apply multiple tests, we can apply just a few tests, we may even apply no tests. Some equipment might be visual inspection only. So from that side of things, it is important that we actually just understand why we carry out tests. We don't do tests for the fun of it, we do tests to actually determine what the safety status of the equipment is. So if a test isn't going to tell us anything about the safety status of the equipment, there's no real point us carrying that test out. So from that side of things, we need to do just the test that we need to get the full picture. But sometimes, quite often, people make the mistake of missing out tests that could have potentially detected a fault because they're just not aware they're available or they just don't think it's necessary. So again, this is a really important session to pull the two halves together, the core basic test and the advanced tests, to give you this full menu, for want of a better term, that you can then choose from when you're testing equipment. So what we're going to look at in this section is the different ways to test insulation. Quite often with insulation testing, people get confused, or they get put off by the different terms, and they don't understand why you do one over the other. Do we do this one instead of this one? Why would I want to do this one instead? And all that sort of thing. So I'm just trying here to simply demystify that a little bit for you, the different ways that we check insulation. Insulation is an essential safety measure used in electrical equipment. Knowing the different methods for testing insulation is a key part of being competent. Each test method has its own strengths and weaknesses. We can apply multiple tests to fully test more complex equipment. Always take appropriate safety precautions when testing insulation. So with all that said, if we look at the table here, what we've got in the table here is effectively all the different options that we've got available to us when we're actually carrying out testing on insulation of equipment. Some of which we'll do, some of which we're actually advised not to do. So it's just a matter of us looking into it and deciding which is appropriate for the equipment that we've got. Now, generally, the way this table is laid out, at the top of the table, you'll notice that we've got typical test voltages are higher. So the higher test voltages are towards the top of the table, and as we go down the table, the test voltages get lower. Now, the test voltages are important because the more voltage we apply, the more stress we're putting on the insulation. So the more stress we're putting on the insulation, the greater the test we're applying to it, the more robust test we're applying to it. So if we apply, for example, 3000 volts there, using a dielectric strength test to insulation, as a manufacturer might at the end of a production line, that's really giving that insulation some stress. And if there is a fault in there, chances are we're going to find it. We're going to get it to break down. We're going to find that fault. Whereas if we're just applying at the other end of the spectrum, we're applying 40 volts to that, you can see we're not applying the same amount of stress. Now, that's good and bad, because if we're applying stress to insulation, we could actually damage the equipment. If we've got sensitive electronic equipment and we don't apply the test in the right way, we could damage that equipment by doing a dielectric strength test. Whereas applying something like a substitute leakage test is what we refer to as a soft test. It's not going to actually risk damaging the equipment. So there's also, as I've mentioned in the bullet points there, there's also safety considerations to be taken into account. If we're going to apply, thousands of volts to this piece of equipment, that's potentially dangerous for the tester. So the person doing the testing, that is. So we need to take safety precautions. We need to have a proper safe test area set up. We need to have insulated mats. We need to have barriers. We need to have all of these things set up to be able to do that. So it isn't necessarily something that you can just do, in somebody's office, say, or a workshop. You'd have to have a designated test area set up for doing that. So if we look at the options we've got on here, we've got the dielectric strength test. Now, this is sometimes known as high pot testing or flash testing. You might have heard the term flash testing. And a few years ago, going back to the sort of maybe the second edition of the Code of Practice, flash testing, dielectric strength testing was mentioned as part of pat testing. And there are still some companies, particularly hire companies, tool hire companies, who still carry out flash testing as part of pat testing because they believe that it's worth doing that. They've got equipment that's quite resilient, but it's going to be used in harsh environments. It's high risk equipment, so they would still carry out dielectric strength testing. Currently, the IET Code of Practice, the 4th edition that we're working to now, says don't do flash testing for in-service inspection and testing, because they've taken the judgment that realistically it's above and beyond what we need to do, and the risks of carrying it out correctly and safely outweigh really the benefits we get from doing it. So the current guidance within the IT Code of Practice is we don't do flash testing, but there are companies who do, particularly like I say, tool hire companies. It's still very, very common because they deem that it's necessary to do that. So really, dielectric strength testing or flash testing would be an example of a very hard test. It's going to be quite rigorous on the equipment, but it is going to find those faults. It is really going to put that equipment under some stress. But again, you do run the risk of damaging the equipment or potentially damaging yourself while you're doing it. Going down to the next step, we talked about last week, we talked about the insulation resistance test, and we talked about the options to do a 500 volt test, or if we've got sensitive or surge protected equipment, we might do that at 250 volts. Now, the insulation resistance test is pretty much the standard, the standard pat test that we would carry out. And the 500 volt test does put equipment under stress. There is the possibility, as we discussed last week, of potentially damaging sensitive equipment by doing the 500 volts test. But of course, we're talking about a voltage that's more than twice the supply voltage. So again, it's giving that equipment a certain amount of stress there to actually find those faults and give it the opportunity to fail under test conditions rather than fail in real life. But we've got those two options there for insulation resistance, 500 volts or 250 volts. Now, something we're going to be talking about a lot more today is actually doing what's called a leakage test, protective conductor or touch current tests. Now, these tests use the mains supply voltage as the test voltage. So they apply 230 volts mains, or the pat tester applies 230 volts mains to the equipment, and the equipment actually runs as if it's normal. Normal equipment, it's there, it's running as normal, and we measure the leakage currents either coming back down the protective conductor or via the test probe to actually see, are there any fault currents present? And the logic is that if there's fault currents present there, they must have leaked through the insulation, and therefore that tells us we've got an insulation problem within that equipment. So although they're not insulation resistance tests or insulation strength tests, they're doing the same thing. The only difference is we're measuring in current rather than resistance. But as we looked at in previous sessions with Ohm's law, that's just an equation. So we can work out the insulation, we can work out the current. It's basically just two halves of the same thing. So the actual protective conductor current tests and the touch current test give us options to actually test equipment. Now, again, this is a softer test. We're never going to, or hopefully never going to, damage equipment by supplying its normal supply voltage to it, its normal mains voltage to it. It's not like we're putting 500 volts in there. We just turn the thing on normally and we're measuring its condition. The great thing with the leakage test, the protective conductor or touch current test, is that they're actually just really getting the equipment to do what it would normally do. So we can actually operate that equipment under normal conditions, and we're getting pretty accurate picture of the safety of that equipment. Of course, we've got to think about, as we said in the bullet points there, the safety considerations of this, because if we're taking a piece of equipment in potentially unsafe condition and we're applying 230 volts to it from the mains, that could be quite dangerous. Even if the equipment hasn't got a fault, it's still going to do what it normally does. So if it's a drill, it's going to spin round. If it's a kettle element, it's going to get red hot, and so on and so on. So we do need to think about the precautions that we do when we actually apply these tests. And it is very much a trade-off between the strategies that we use. And we'd normally always advocate carrying out an insulation resistance test anyway before you did a protective conductor current or touch current test. Because what you're doing is you're checking the input side of the equipment and you're sort of verifying at least as much as you can the safety of it before you carry out those tests. Now, the final option on there, and we'll go into this in more detail later on in the presentation, is the substitute or alternative leakage test. Now, this uses a test voltage of 40 volts AC generated by the tester. This can be a battery-powered test, so the tester can do this off battery power or off mains power, but it's not using mains voltage. It's actually generating this 40 volts AC within the tester. And then what we do is we carry out the measurement, very similar to protective conductor or touch current tests, and then we scale those readings up to what we would have got if we had have applied mains voltage to it in the first place. So again, this is a very sort of super soft, safe test that we carry out. But we need to be aware of the different options that are available. These are all ways of judging the quality of the insulation within a piece of equipment. They will all detect faults to a certain level within the equipment, and certainly the more severe faults that you'd be expecting to see, these would pick those faults up. But again, it's where do we go on that scale? Obviously, ideally, we want to be towards the top end of the scale of putting that equipment under rigorous testing and getting reliable, results after applying rigorous tests. But we've got to balance that, particularly nowadays, with damage to sensitive equipment. And we're getting more and more sensitive electronic equipment in the workplace. We're getting more equipment with, electronic starters on there. We're getting more equipment with contactors and things like that, and surge protection, certainly. So again, the test strategies have changed over time. If you go back in the day for PAT testing, it was all flash testing, 500 volts testing, because all we were testing was, kettles, drills, toasters, things like that would take it. But now the modern workplace has got way more electronic equipment in there, and we've had to adapt our test methodologies a little bit. So hopefully that's just giving you a bit of a sort of an idea of the options on there. As I say, we're going to talk today about the sort of the bottom half of that table, and last week we talked about insulation resistance. But flash testing is there as an option, but again, the code of practice advises against that for in-service inspection and testing. But you can, if you do feel that the risk warrants it, as I say, is quite common in the tool hire sector, you can actually carry out those tests if you wanted to as well. So leakage testing. Leakage testing, the name leakage testing covers really sort of a wide range of tests. So generically known as leakage tests, there are a series of tests that can check the effectiveness of an equipment's insulation by operating the equipment and measuring the levels of current that leak, for want of a better term, through the insulation. The leakage tests we're going to discuss today are listed below. So we're going to have a look at what's called the protective conductor current test. We're going to have a look at the touch current test, and we're going to have a look at the substitute leakage test. These are all generically known as leakage tests, and there is sometimes different names for these, but basically that's the current names as they're listed in the code of practice. But you will see sometimes some PAT testers and some manuals and things like that will refer to them by different names, but they're generically known as the leakage tests. So leakage tests are often used when the insulation resistance test is not able to fully test the equipment. For example, where there's a contactor or relay used in the mains switching arrangement of the equipment. So typical example, just imagine something like a computer. To turn a computer on, you press the electronic start button on the front of the computer. That then kicks the power supply into life. The power supply then boots up and starts working, and away you go. Now, if you were to just do an insulation resistance test on that piece of equipment without turning it on, all you're really doing is you're checking up to the input side of the power supply. If there was excessive leakage or a fault within the power supply, chances are we might not detect that, because effectively the power supply is not connected until mains is applied to it. So actually the button on the front of the computer is not a mains button. There isn't 230 volts run to that button like a switch on a kettle, say. It's a soft button. It's a button that electronically drives the power supply. So for us to fully test a piece of equipment like that, just doing insulation resistance test only tests so far. So in that case, we might want to apply a leakage test as well to fully test that equipment past the input stage of the power supply and actually get the full picture of it. So other equipment that fall into this category, we get things with stop-start buttons. So maybe in a workshop you might have something like a sander or a grinder or a saw where you've got a stop-start button. That may have a contactor built into it, like a relay built into it. So again, it's only going to turn that piece of equipment on when you turn it, when you've got mains power applied to it. Even later in this session, we're going to talk about things like RCDs. A lot of RCDs won't switch on unless there's mains power applied to it. So we might want to do a leakage test for equipment that's actually got RCDs protecting it, because again, we need that mains to be able to turn the thing on. Leakage tests should always be preceded by an insulation resistance test to test any faults present in the input part of the device before subjecting it to the supply voltage. Yeah, we always want to apply an insulation resistance test first, even if it's only at 250 volts. The reason being, if we've got a fault with, say, the cable, we could detect that with insulation. So if we just said, oh, we're not going to do an insulation test, we're just going to go straight into a leakage test, we're applying mains to that, and potentially, we're going to get a bang, we're going to get a fault straight away. Whereas we could have detected that if we tried with the insulation resistance test. So it's always advisable to start off with an insulation resistance test, because again, that's it's a safe voltage pretty much generated by the tester. It's generated by the tester. It's not a mains voltage. It's a voltage generated by the tester, so the current is limited and things like that. And what we can do then is actually get a picture of that without putting ourselves at serious risk. Whereas if we're taking a piece of unknown equipment and the first test we're going to do is plug it into the main supply, if we can avoid doing that, we really should. So we always advocate doing an insulation resistance test before we do any of these mains powered tests. Great care must be taken when applying leakage tests, because the equipment will operate, causing parts to move or create heat, for example. Any safe systems of work relating to the use of the equipment must be followed, and it may be necessary to enlist the help of a trained user to help in the testing process. So yeah, we might have grinding equipment. So you might have a grinder, and you might not be trained in the safe use of that grinder. You might not be approved to actually remove the grinding discs. So if we're carrying out a test on a grinder, common sense would say that we take the grinding discs out. If we're going to carry out a test on a saw, we take the saw blade out. So we're minimizing that risk. But again, we might not be trained to do that. We might not have the PPE. We might not have the certificate for doing it. So again, no problem. Get the user, a trained user, to help you to carry out that test. So we're making sure that we're adhering to the precautions. Another thing to mention is just the duration of test, how long you apply these tests for. Quite often people will apply these tests for, say, 5 seconds. Now, that could be okay if it's just a straightforward something like a heater, 5 seconds, the elements come on, get the leakage reading, turn it off again, great. But if you've got something like a computer, 5 seconds is probably enough for it to just start booting up, and then you effectively yank the power out of it, and that could cause damage to the equipment. So always think about the duration of these tests, how long you're going to apply the tests for, because you need to apply the test for a long enough period of time to test consistent operation and to test the equipment in all its different modes of operation as well. So always apply the test for the right duration. Don't just think, how quick can I get away with this? Because you might not actually be allowing the equipment to fully operate, and you're not going to find faults. So actually you're just doing a test that's pointless there. But always think about the safety when you do mains powered tests, because it can be a big problem. I mean, particularly something like a kettle, for example. If you haven't got water in there, the element's going to glow red hot. And I've seen loads of people who've actually, they've still got the crock clip clipped onto the element from doing an earth continuity test. They go straight into the leakage test, turn it on, and it melts the crocodile clip to the element with inside the kettle. And there's a load of sort of smoke and burning smells, and not very, very nice. I've also seen people test grinders. I've seen somebody test a 9-inch grinder where they just left it on the desk with it switched on, because they want the on switch switched on, got to the leakage test, and it said, is it safe to turn it on? They just went, yes, hit the button, and the grinder spins round and shot off the desk onto the floor. So those sort of things, we've got to be very careful to avoid that when we are applying these tests. So always think about the precautions before you apply the test voltages to it, could be because it's too late afterwards. Also, another thing we've got to look at here, it says also avoid testing equipment with high inrush currents or starting currents. This can damage your PAT tester. Yep, you've always got to think about this, because you're running the test through your PAT tester. Whatever current your equipment draws is going through the relays inside the PAT tester. It's been switched by the PAT tester. So if you've got a piece of equipment, now that equipment might be 13 amp rated, but when you turn it on, it can draw a huge amount of current for a short period of time from the main supply. Now, if it's going to draw that through the PAT tester, that could actually blow the fuses in the PAT tester. It could damage the relays in the PAT tester. And we have had this in many cases where people are damaging the PAT testers and they don't know why they're doing it. They don't know, oh, it just keeps blowing up. It just keeps going wrong. And this could be they're testing things like large circular saws, pressure washers, big industrial pressure washers, lighting has high inrush current. So big studio lights, big theatre lights, things like that, where when you first turn it on, the current suddenly shoots up to 50, 60, 70 amps maybe. That's pulling that through the pat tester. Now, the poor old pat tester is rated to cope with certain amounts of inrush currents. But if you're doing that all day, you're doing 100 of those all day, don't be surprised when the relays burn out or the fuses start blowing or, you test a big piece of equipment. So always think about what's the level of current that's going to be drawn by this thing, because it's got to go through the pat tester. Normally, it's fine. You've got it plugged into the mains. Great. No problem at all. It draws a bit of extra current for the mains. That's okay. But when you're pulling that through the pat tester is only rated for certain levels of current. And especially, like anything, if you just keep doing that over and over and over again, you're going to damage your pat tester and you're going to have to send it in for repair and you're going to get a bill. So always think about equipment starting currents and inrush currents. And if you're not sure, we speak to the manufacturers or, potentially the strategies where you could measure the current and things like that if you needed to. But always think about it when you are doing these tests, because quite often people don't understand that, they can actually damage equipment by doing these tests. So always think about that when you are performing a leakage test. So the first one we're going to have a look at is the protective conductor current test. And the protective conductor current test is used to test Class 1 equipment. Obviously, Class 1 equipment is equipment with a protective conductor. We're going to do the protective conductor current test. So it is a type of leakage test, but it's the protective conductor current test. So in this case, the supply voltage, normally 230 volts AC, is applied to the equipment via the pat tester. The equipment is operated for a period of time, and the current flowing in the protective conductor is measured. So in theory, what we're doing is we're powering up the equipment and we're measuring what current flows back down the earth wire, the protective conductor. And in theory, that equipment must have come from somewhere. That current must have come from somewhere. And where it's come from is it's leaked through the insulation. In theory, that's the way it works. So most pat testers use the differential current measurement, where the line and neutral currents are measured and the difference is taken to be the leakage current. So some people automatically assume that we just measure the current in the protective conductor. Now that's one way of doing it. You can just measure the current in the protective conductor. But by measuring the differential current, you're actually getting the total leakage, for want of a better term. You're getting all of the leakage, because the difference between the line and the neutral is all of the leakage. Whereas if leakage was going down a parallel path or something like that, say, we wouldn't necessarily pick that up by just measuring the protective conductor current. So say if you've got it sat on a metal bench or something like that and some of the equipment was finding its way back to earth another way, you wouldn't necessarily pick that up with a protective conductor current. So it's quite common nowadays to do this as a differential measurement. We measure the line current, neutral current, not one off the other, and that's taken to be the leakage current or the total leakage current from that side of things. So many types of equipment will have natural leakage currents, which are present in normal operation. The competent person must be able to distinguish between these normal, safe currents and the leakage currents that are caused by a fault. So this is a big problem with protective conductor current testing. It's only really protective conductor current testing we have the problems, because generally this isn't something you'd see on Class 2 equipment. It isn't really you don't get natural leakage currents to expose parts in Class 2 equipment. So with protective conductor current testing in Class 1 equipment, part of the reason for the earth being there is functional earthing. The earth wire acts to allow us to filter out noise and disturbances within the electrical installation. So a lot of equipment, particularly where we've got electronic power supplies, stuff like computers and things like that, there will always be a small amount of what we call natural leakage current. That's leakage current that's traveling back down the earth wire that's meant to be there. It's part of the initial design. The designer is using the earth wire to get rid of some of the currents that they don't want. So if they're filtering out noise, for example, or interference, some of that current may well go back down the earth wire, down the protective conductor. So theoretically, you would think any current down the earth wire is bad. It must have leaked through the insulation, in which case there's problems. But it could have come through components, electronics within there and things like that. So it could be designed. So this is where it's quite important to look at your test history, to look at, when you test a piece of equipment in as new condition, recording down the leakage current. So if you know there's always 0.1 milliamps or whatever it is on there, then you go, right, I know when it was new, this has always got a certain amount of leakage. There was always a little bit of leakage in there. So that when you come to test it and suddenly that leakage has gone up, then you go, hang on, there's something different here. There's something I can see based on the previous test results and what I'm getting now that there's additional leakage. There's something, there's a problem I need to investigate here. So it is important, that test history, knowing what it normally reads like, knowing what typical equipment's, if you're testing several drills that are the same make, the same, manufacturer of drill, again, the natural leakage current should be about the same. So you can use comparisons through, similar products and similar equipment to actually try and establish the natural levels of leakage currents. And once you know what the natural levels of leakage currents are, then anything that's more than that generally will give a flag. So if we just go on to the next slide here, you can see a bit of a diagram. So on the diagram that I've drawn here, you can see that we apply the mains voltage, normally 230 volts mains, but it could be a 110 supply or something like that. Obviously, current goes down the line, through the load, and back out down the neutral. And under normal conditions, as I say, natural leakage currents aside, the line current would equal the neutral current. So the residual current or the leakage current would be zero. Now, if we've got a problem with the insulation, you can see there on the diagram, we've actually got that little zigzag there, that little red zigzag between the load and the exposed, the earth metal parts. So we've actually got a little breakdown with the insulation. That could be damp in there. That could be a stray bit of metal got in there, some dust, some, conductive dust, bit of wire wool, whatever it is. Something's got in there and broke down between the live parts and the earth parts. So then we've got leakage. So what's going in on the line is not what's coming back out on the neutral. There's a difference between the two. And that is then going back down the protective conductor, down the earth, and that is our protective conductor current. So we're actually learning about the condition of the insulation, and potentially this might have been picked up by an insulation resistance test. But as we said, if we've got a contact or we've got something on the mains, that wouldn't have been picked up by the insulation resistance test. So we could have a faulty piece of equipment that we've put into service because we just didn't know. So the supply voltage is applied to the EUT. Any difference in the line and neutral currents are shown as the protective conductor current. And just be aware with the pass-fail limits there that portable and handheld equipment has a tighter limit than other Class 1 equipment due to the increased risk posed to the user. So you can see the pass-fail limits there. So portable or handheld equipment really is our high-risk equipment. So it's likely to be in somebody's hand when it goes wrong, or somebody's going to be moving it from place to place. So the pass-fail limit for this type of equipment, the leakage has got to be less than or equal to 0.75 milliamps. That's 3/4 of a milliamp. Now, the perception level for electric shock, for a mains electric shock, is about a milliamp. So it's about a milliamp. You'd start to feel a tingle if you touched it. So we're saying on this, we're actually setting the pass-fail limit less than 0.75 of a milliamp. So less than 3/4 of a milliamp. So this is below the level at which you'd even start to feel it if it was you were to touch that thing and you were getting a shock from it. Now, other Class 1 equipment, so now we're thinking about stationary, we're talking about movable equipment, we're thinking about maybe computers and things like that. They're allowed to have a pass-fail limit of less than or equal to 3.5 milliamps. So 3.5 milliamps. That's still, a safe level, still a very safe level, but it is above the level where you would start to actually notice it. You would actually start to feel a tingle at that level. But it's still a very safe level in there, but you can see it's significantly higher than handheld or portable equipment. And this is quite often sometimes where people get themselves into problems, particularly when we've got things like our manual tests, like the prime tests, where on the prime tests, the pass-fail leakage limit on the prime test 100 is set to 0.75 milliamps because you can't change the test sequences. So we've set it to the safest limit possible. We've set it to the safest limit on there, which is 0.75 milliamps. Now, we could have changed that. We could have had that at 3.5 milliamps, but then effectively we're actually passing things that maybe should have failed. So always watch out for that. If you have got equipment that isn't portable or handheld, and your Prime Test 100 is failing that equipment, just have a look at the leakage readings, because is it because it's actually coming in at 1 milliamp, which is still a pass for equipment that isn't portable or handheld, but the tester is just applying that 0.75 milliamp limit. So you do just need to be careful to make sure what limit your PAT tester is applying, is it applying it to the right equipment? Because portable and handheld equipment should be tested at 0.75, but everything else is less than or equal to 3.5. So we've got quite a bit of extra current there that we're allowed to use on that type of equipment. So that's protective conductor current testing. Now, if we just go on to the next slide here, you'll see how we connect up the PAT tester. So you'll notice that the main supply is connected to the PAT tester, and the test connection is made by plugging the equipment into the EUT, the equipment under the test socket on the PAT tester. So you can see there we've got the black mains lead into the Apollo, we've got the toaster there plugged into the test socket, the EUT socket on the Apollo, and the Apollo is going to pass that mains current through to the tester, through to the equipment under test, the toaster, and measure the leakage current. Now, obviously, the thing we need to remember there, like the pictures there and the little measures there, is we do need to have the equipment turned on. So during the test, we would actually need to, once the test has started, we would need to actually turn the equipment on to make sure that we are fully testing the equipment there and actually test it. Because if we don't turn it on, it'll do the test, but it's still only measuring up to the switch and not actually fully checking the equipment. So always make sure equipment is switched on at that point. And as I said, obviously make sure we've applied the safety precautions with that. So the test connection is relatively simple there, because we've got everything we need in the plug. We've got the line, we've got the neutral, and we've got the earth. So it's all there for class 1 equipment. We just need to connect the PAT tester to the mains. And obviously, as I said before, have a think about things like inrush currents and stuff that could cause problems, because obviously last thing we want to do is actually damage the tester. So the next test we're going to have a look at here is touch current testing. Now, touch current is usually used for class 2 equipment. It's the only strategy, obviously we can't do protective conductor current testing on class 2 equipment because there's no protective conductor, but you could, in theory, if you wanted to apply a touch current test to class 1 equipment, maybe if you wanted to check certain parts on there. But normally, protective conductor current testing is what we do on class 1, and touch current testing is what we generally do on class 2 equipment. So in this case, the supply voltage, normally 230 volts AC, is applied to the equipment via the PAT tester, and the equipment is operated for a period of time, and the test probe is used to measure the currents that would flow if the user were to touch exposed parts. So that's the important thing on here. What we're doing is we're actually measuring exposed parts. So if I've got, say, the body of the drill there on the slide, I'd actually be measuring to the body of the drill. So what we're saying is if I was the user and I was using this drill and I was to touch that part, what current would flow down my finger? What current would flow through me if I were to touch that part while this thing was in operation? So whereas before we were looking at what current would flow down the protective conductor, touch current is saying if I were to touch that bit there, what would flow through me? So unlike the previous test, the touch current test requires a test probe. So we're actually using a test probe. Instead of using your finger, we're using the test probe to simulate if I was to touch that bit, we put the test probe on. But also we use a 2K ohm body model to simulate the typical resistance of the human body. So my body will have resistance, and on average that realistically is about 2,000 ohms. So what we're saying is that if I applied the test lead, the test probe, to a certain piece with a 2K ohm body model in line with that to limit the current to what is, to simulate what it would be really if it was to travel through me. Because remember, my body isn't 0 ohms. If we just use 0 ohms, we could say, oh, actually, there's loads of current there. But that's not what would go through you if you were to touch it. What would go through you if you were to touch it would be the current limited by your body resistance. So that's why we use this 2K ohm body model, this 2K ohm resistance in series with the test to actually give you a realistic simulation of what you would get if you were to touch those parts. Now, the other thing we have to think about is it's often necessary to repeat the test with the test probe connected to each exposed conductive part. This ensures that all parts of the equipment have been tested for the presence of fault currents. Yeah, so actually we might have the body of the equipment, we might have the handle, we might have some screws. So testing one doesn't necessarily mean that they're all okay, because if you've got a piece of class 1 equipment, generally anything that needs, to be earthed for safety reasons is connected to earth. So effectively it's testing all of those things in one go because they're all connected to earth. That's the point. But with touch current, we might have several things that the whole point of them is that they're not connected to it. They're not connected together for safety reasons. So we may need to test, different screw heads. We may need to check the body and the handle and the screws. So it's quite common with this that we would need to actually either repeat the test or run the test for a period of time and move the test probe during the test to actually check each of those pieces in turn. So we need to actually do a little bit more work with this one to make sure that we've fully tested each bit. And that's a common mistake a lot of people make, is they just go in, dive in, yeah, we've checked that bit, it's fine, yeah, that's okay, and forget about the rest of it. So I've put a little diagram up here again, very similar to what we had before, but what you can see in this case is we've obviously got the double insulation there, we've got the basic insulation, the grey insulation, we've got the supplementary insulation, which is in red there. And what we're saying is that we've got current coming down the line, should be going back down the neutral, but in this case, what we're saying is we've got a breakdown between the load and the exposed part, in this case the drill chuck. And what we're looking to see is if we applied the test probe to that drill chuck, what current would actually flow down through our body model and actually give us the touch current measurement, the current that would flow through my body if I was to touch it. Now, obviously, one obvious mistake you can see on here is it would be quite difficult to actually test the drill chuck when it was spinning round. So again, this is just an example of what you would the sort of theory of it, but again in practical you can see the practicalities of doing that. So actually, how would we do these? And you do see some people with test probes that have actually got sort of like a bristle brush on the end, like a metal bristle brush, for doing that sort of thing. But again, we might be able to use other test methods, for example something like the substitute leakage test, to better test these parts. But you get the idea that any exposed part, not necessarily just drill chucks, but any exposed parts on class 2 equipment, we'd actually carry out this test, and we're simulating what would travel through me, what would travel through my body if I were to touch that bit there. So the supply voltage is applied to the equipment under test. Any difference in the line and neutral currents are shown as the touch current. So again, this is still generally a differential measurement, but obviously the differential current is also the touch current. The touch current test simulates the current that would flow through the user if they were to touch exposed parts. So you can see what's going on here. And again, safety precautions, we need to make sure that if we are doing these sort of tests, that we have taken precautions exactly the same as any of the other leakage tests. Now, because this is class 2 equipment, this is double insulated equipment, we're not expecting any leakage to any exposed parts really from that side of things. We're just not expecting any leakage. So the limit is actually less than or equal to 0.25 of a milliamp, less than quarter of a milliamp. So we don't expect any natural leakage currents because that's not how this equipment's designed. Any of these parts, we're not using it like we use a functional earth or a protective conductor in class 1 equipment. We're not expecting any currents on any of these parts. So less than or equal to 0.25 a milliamp is the pass-fail limit for the touch current test. So we can see here the test setup. We've got the Apollo there. That's connected to the mains via the black mains lead. We've got the red test lead connected to our exposed metal part on the lamp. And we've got the plug for the lamp connected into the EUT socket on the PAT tester. Obviously, we need to remember to switch the lamp on as well. So we're actually fully testing past the switch. So the main supply is connected to the PAT tester. The test connection is made by plugging the equipment into the EUT, and the test probe is connected to the exposed conductive part. And just reiterating there again, the pass-fail limit that we're looking for is less than or equal to 0.25 milliamps. So relatively straightforward test setup there. You can see how these things are connected. and we carry out the test for a period of time. Again, doesn't need to be too long for this, just enough time to turn the lamp on, and we get our reading, hopefully less than 0.25 milliamps. Relatively straightforward test. So now we're going to actually talk about this thing called a substitute leakage test, or alternative leakage test to give it another name. The substitute leakage test is effectively a battery-powered leakage test that can be applied to either Class 1 or Class 2 equipment. 40 volts AC is applied to the EUT, the equipment under test, between the live conductors. That's the line and the neutral joined together. So we join the line and the neutral together, so we're actually applying that similar to how we would with an insulation resistance test. So we apply the test between the line and neutral joined together, live conductors, and the earth conductor for Class 1 equipment, or via the test lead and probe to expose conductive parts for Class 2 equipment. So very similar how we would carry out the protective conductor or the touch current tests, or how we would do actually an insulation resistance test, for example. So there's nothing massively different or difficult about the test configuration. The results obtained are scaled up to simulate what the expected reading would be at the supply voltage. So we're carrying out the test at 40 volts, and then we're scaling that reading up to what would we have got at the 230 volts, 240 volts, the mains voltage that we would have seen. So again, that's the difference with this test. It's done at 40 volts, but we're scaling it up. We're effectively simulating what we would have got if we had have applied mains voltage to it. So as an AC test, remember the insulation resistance tests are DC. As an AC test, this may detect faults not seen during the DC insulation resistance test. So that's the important point. Sometimes people say, well, why would I do the substitute test? What does it add? Well, being an AC test, we're actually using alternating current. So it's similar to what you would be using if you were supplying mains voltage to it. So there are faults that can be detected using alternating current that wouldn't be seen just using pure DC. Care should be taken when interpreting the results. Some equipment can read artificially high due to the joining of line and neutral. Yeah, this is quite a typical one that some people see. If there's particularly things like capacitors within the power supply, and things like washing machines are well known for this, and dishwashers, where what you get, because we've joined line and neutral together, we're actually getting the capacitance joined together effectively. We're getting the capacitance that would be between line and earth and neutral and earth is actually then joined together. So we're getting effectively the double the effect. So we see double the leakage. So it's quite a common thing to see higher than normal leakage readings on equipment that's got these electronic power supplies with capacitors and things like that in there. So always be careful if you are carrying out these tests, because sometimes people just assume that the equipment's faulty or the pat tester's faulty or whatever. And it's just the effect of the substitute leakage test, because we join line and neutral together. That's not obviously what you'd have under normal operation. So if you're not certain about this, obviously you can do an insulation resistance test, but you can also do one of the mains powered leakage tests that we talked about to try and verify whether it is a true reading or whether it's actually just due to the way the test works out. But it's one of those things that as a competent person, if you're aware of it, you can deal with it. The other thing that impacts that as well is with, as we've mentioned, if your pat tester is set to, for Class 1 equipment, to pass-fail on 0.75, and then you get this doubling effect as well, you might be getting, say, a slightly higher reading, say 1 milliamp or something, and your tester's failing it, but it's only failing it because it's an artificially high reading. So always just be careful with that. That's something just to be aware of when you're applying the substitute leakage test. It's a great test because it's something we can actually apply. It's battery powered. It's a very soft, safe test, so you don't need mains to carry out the test. It's also not going to damage equipment. It's not going to actually turn it on and spin it round and all those sort of dangerous things. So where we were talking about checking to the drill chuck, for example, a substitute leakage test would be a good option in that case, because it's not actually going to spin the drill chuck round, so we can do a measurement to it. So there's a lot of advantages to doing the substitute leakage test, but like all these, we said they have strengths and they have weaknesses. So we just need to know where we're applying it and why we're applying it in certain ways. So always just think about that when you are doing a substitute leakage test. So the test connections, test method, and also the pass-fail limits for substitute leakage testing are exactly the same as that for protective conductor current or for touch current tests. So same pass-fail limits, same connections, same methods, but no connection to the mains is needed, and the test can be powered by PAT testers, by the PAT tester's battery. So you'll see here in the diagrams that I haven't actually connected the mains up to these testers. They can do the substitute leakage test as a battery powered test. So if you haven't got access to the mains, or you don't want to get access to the mains, this is a good option for leakage testing, but it's a battery powered leakage test as opposed to actually powering it from the mains. So again, everything else is the same. The test connections, putting the test probe on for class 2 equipment, or just using the plug for class 1, and obviously carrying out the tests exactly the same as we would do with the other leakage tests. Same pass-fail limits, but this just gives us this battery-powered option. So the last thing we're going to look at today is the residual current device testing, actually testing RCDs. So a residual current device, or RCD, is a device that provides the user with additional protection against electric shock. Unlike overcurrent devices such as fuses and circuit breakers, the RCD operates on residual current. That's the difference between the line current and the neutral current. This means that the RCD can be very sensitive and therefore increase the user's shock protection. In the UK, RCDs with operating currents not exceeding 30 milliamps are specified for additional protection against electric shock. To test RCDs, we apply currents of 1 times and 5 times their rating. So obviously 1 times the rating of a 30 milliamp RCD is 30 milliamps, and 5 times the rating is 150 milliamps. And we measure how long they take to trip. We do each test twice. Once for the positive half of the AC supply waveform, what we refer to as 0 degrees, and once for the negative half, what we call 180 degrees. So when we do these tests, we perform it with the test starting just as the waveform's going positive at the 0 degrees point, and just as the waveform's going negative at the 180 degrees point. And that means that we can actually identify any faults where the RCD is out of balance, because what we don't want is an RCD that works perfectly on the positive side of the waveform but doesn't work on the negative side of it, and it's just look where the waveform is when the fault occurs. So from that side of things, we always test both. We test it at the operating current, I say the 1 times test, 30 milliamps, and we simulate a higher fault of 5 times the rating, and obviously at that rating it should trip even quicker. So following the tests, we also use the test button to check that it functions and trips the device. So it's a functional check. Pressing the test button is a functional check, and generally we do that after we've done the other tests. And the reason we do that afterwards is because we don't want it to influence the results. RCDs can actually stick, they can corrode, they can stick. And sometimes if you just go and you press the test button, the RCD will shake itself loose and it'll pop out and it'll trip. You won't notice the difference, but if you'd have tested it, it would have failed. But what you've done then by pressing the test button is you've released it. So then when you do the tests, it's fine, but it's not making you aware that the RCD's got a problem, that there's internal corrosion, that it's sticking, that it might have got full of dust and God knows what. So it's always better to do the measured tests first, because then you will see if there is any of those faults in there, and then just press the test button afterwards to check that the test button operates, because that's what we're doing. We're just making sure that the test button operates, it trips the RCD, and then users, when the users do a user inspection, a user check, they would just use the test button as part of their user check to make sure it works. They wouldn't actually test the tripping times like we would when we're doing a full combined inspection and test. So that's why we always say check the test button at the end, because we don't want to influence the other results by just pressing the test button, and we've masked a fault that was there and we've hidden it, and it'll obviously then just come back after a little while. The thing will corrode up again, it'll rust up and it'll stick. So Always an important point that we do the functional check afterwards, not before we've done the measured tests. So the main supply is connected to the PAT tester, so you can see the black lead there, and the RCD is plugged into the EUT, the equipment under test socket. The red IEC test adapter, IEC lead there, is connected between the socket on the RCD and the lead test socket on the PAT tester, the IEC socket on the PAT tester. Now this is exactly the same if you've got an RCD extension lead. We just put that in between. We put the red lead into the RCD extension lead. We connect the RCD extension lead plug into the PAT tester. So what we're doing is we're creating this loop inside the tester. So the mains is coming into the tester, but the test is being carried out internally within the PAT tester. Now, some older PAT testers will require you to connect the RCD to a main socket outlet. So you're not connecting it to the outlet on the PAT tester, you're plugging it into a socket on the wall. Now, be warned that this method risks tripping RCDs protecting the fixed installation and cutting off power to parts of the installation. So a lot of PAT testers have come unstuck testing RCDs where they plug the RCD into the wall, they plug the PAT tester in, they press test, and all the lights go out. We've tripped off part of the building. You've got angry customers, potential danger there. You know, it's been plunged into darkness. People have lost their data on the computers, all sorts of things. So modern PAT testers now, and obviously, you know, with Seaward's Apollo here and our Prime Test 250 Plus, we actually do this test internally within the PAT tester. It's isolated from the mains. So you're not actually going to cause this, what we call nuisance tripping, when you're carrying out RCD tests. Now, it's a big benefit doing that, whereas some of the older PAT testers, you have to plug the thing into the wall and you risk that nuisance tripping. So just be aware that that's something that needs to be looked at. So here we're going to take a look at the pass-fail limits. Each RCD is subjected to 4 tests, 2 at the rated current and 2 at 5 times the rated current. So the rated current of normal RCDs is going to be 30 milliamps, and 5 times that is 150 milliamps. So what we do is we'd actually carry out a 1 times test starting at 0 degrees. So that's to test the positive half cycle. And then we do that again at 180 degrees to test the negative half cycle. We then repeat those tests at 5 times the rating, so with a test current of 150 milliamps starting at 0 degrees, again to test the positive half, and at 180 degrees, again testing the negative half. The tripping times must comply with the pass-fail limits in the table to the left. So if we have a look at the table there, what you'll see is that at the 1 times rated current, the 30 milliamp tests, we've actually got 2 different pass-fail limits, and it depends what British standard the RCD has been manufactured to. So the normal plug-in type RCDs that we would come across would be the 7071s, BS7071s, and sockets with RCDs built in would probably be the 7288s. So they're likely to be the ones we're going to come across when we're PAT testing, is the British standard RCDs. So in that case, they should trip for the 1 times tests in less than or equal to 200 milliseconds. So quicker than 0.2 of a second. Generally, they'll be even quicker than that. You know, you'll get some quite low readings. So these are quite high limits, and you'll normally see, you know, sort of maybe 50 milliseconds or something like that as a typical value that you'd expect to see. So for equipment complying with, or RCDs complying with BSEN 7071 or 7288, less than or equal to 200 milliseconds. Now, if there are more sort of mains type RCD, the type of RCDs you'd expect to see in a mains style consumer unit or distribution board, these are to BSEN 61008 or 61009. These have to operate within 300 milliseconds, so less than or equal to 300 milliseconds. Now, when you're testing both of these, if you use 200 milliseconds, generally they'll be within that. If you use 100 milliseconds, they'll generally be within that. So again, you're not expecting huge differences in the results that you get from these, but the standards actually have higher limits there. So for your 1 times tests, whether that's at 0 degrees or 180 degrees, you're expecting to see either less than or equal to 200 milliseconds or less than or equal to 300 milliseconds. Now, the key test that we carry out, the most important one, is the 5 times test, because this is saying, right, how quick can we get it to operate if there's a real fault? Because generally, when we have a serious fault, we're expecting quite high currents. And remember, when we're talking quite high currents, 150 milliamps is still only, 0.15 of an amp. It's not high currents. But again, these are dangerous levels of current. Anything over 50 milliamps is seen as sort of, potentially fatal levels of current. So when we get into fatal levels of current, we want to know that these things operate very, very quickly. So what we're looking for at the 5 times tests is an operating time, a tripping time, of less than or equal to 40 milliseconds. So for the 5 times test, it's got to operate within 40 milliseconds. And that 40 milliseconds is actually 2 waveforms at 50 hertz. So that's where that comes from. So effectively, we're saying within 2 AC waveforms of the main supply, that RCD should have operated and tripped off the supply and disconnected that supply for you. So it doesn't matter what standard it is, whether, what the British standard of RCD is, the 5 times test must operate within 40 milliseconds. And that's really the key one. That's really the important one there for the shock protection. So for 1 times, less than or equal to 200 milliseconds or 300 milliseconds, but for 5 times, less than 40 milliseconds. Now, some older PAT testers you may find might only do a 1 times test. Some PAT testers don't even do that. But it is important now that if you are doing this, the Code of Practice, the 4th edition, does say that we should be carrying out these tests. And we should be measuring the tripping times. So it is important that we do have PAT testers that will actually carry out this type of testing. So RCDs not meeting the required tripping time must be rejected and removed from service. So obviously, if they don't meet those times, it is a fail. It is a fail. And always be careful. If you get an RCD that fails a couple of times and then starts passing, just think about what I was saying before about corrosion, about the thing actually becoming, sort of corroded, gummed up inside, not working very well, being a bit intermittent. Because what we want to rely on this thing. We want to know that this thing's going to operate when we have a fault, not 3 times after we've had the fault. If you have the fault 3 times, it starts to work, then it comes back in. We need to know it's going to work out of the, out the gate straight every time. So when you are doing these tests, if you do notice that it sort of fails a bit and then you retest it, it seems like it's all right, just bear that in mind, because it might be worth actually failing the item at that point, and that might be telling you that the thing's actually, worn out, shall we say, or gummed up or corroded or whatever. So again, that's the test we carry out. Now, you may see some RCD testers do a half times test. So they measure 50, basically it's a 15 milliamp test, a half times test. And the reason that's not included in the actual test specs is because all we're looking for on that test is that the tester doesn't trip. So it's not actually a functional test. It's checking to make sure that it doesn't trip too low, that you don't get nuisance tripping. But because that isn't involved in the safety of it, it's just there to make sure that the thing, doesn't cause anybody a nuisance. That isn't generally included. It's not included in the IET Code of Practice, and it's not really a normal test that we'd carry out as part of PAT testing. Sometimes you'll see that carried out on the fixed installation and things like that. But it isn't a standard one. So if you're wondering where's the half times test gone, generally it isn't a test. It's testing that it doesn't trip. So I could test a switch or a circuit breaker the same way and it still wouldn't trip. So from that side of things, it isn't proving the performance of the device, so that's why it's not included in here from that side of things. So hopefully that's given you a bit better an idea of RCD testing and the pass-fail limits. So we're round to the conclusion. So in this section, we've looked at the advanced PAT tests. We did a bit of a review over all of the tests to see the sequences again and to look at how all of the tests come together into a testing regime. We looked at the options for insulation testing, all the way from dielectric strength testing down to the substitute or alternative leakage test. We looked in detail at what we call the leakage tests, protective conductor, touch current, and substitute leakage tests. And we also finished up with a bit of a look at RCD testing. So next week, we're actually going to be looking at risk assessment in a lot more detail. I know it's something we touched on in the very early sessions in this series, but now we're actually going to have a bit more of a deep dive into risk assessment, because I know that's something that's quite important to people, and particularly those of you who are duty holders as well. It's very important. So where are we at now? Well, actually, it's time for your questions. So I'm going to stop the video, and I'm going to go over to the live version of me, and you can go through and I'll talk through the questions. So for those of you who haven't done so yet, please feel free to type your questions into the chat box, and then obviously we'll go through and we'll talk through that. So thanks very much for watching. It's now over to your questions.